Good morning, everybody. I'm sorry I'm late because I was scheduled to be an examiner for the seminar for a postgraduate student. Unfortunately, it's scheduled at this time, so that I have to postpone the class a bit. Yeah, sorry for that, and thank you for waiting. Yeah, and I expect that you have read the lecture notes. Yeah, which is the continuation from the lecture notes that we discussed last week. Yeah, which is about the ordinary differential equations with for initial value problem. Yeah, in which we discuss about the first method is the Euler's method, in which the Euler's method is the first order method, the first order Runkuta method, and that we can also expand to higher order scheme. So I think we have discussed this last week. Yeah, is it correct?
Yes, ma'am.
Okay. Yeah. So we will do a brief review of what we have learned last week, in which we can improve the Euler's method to the higher order scheme, in which we have the Yun's method. Yeah, we can have the Yun's method, in which this method aims to increase the accuracy of the slope. Yeah, that is used to predict the value at xi plus 1 from point xi. Yeah, so that how to get a more accurate prediction for the slope, so that we can do, for example, in Hume's method, is that we do corrections to the slope, so that the final slope that is used in the calculation is the average slope that is taken from the calculation of the first slope at xi, and the second slope is the slope at xi plus 1, so that the final slope will be the average of the two. And with the midpoint method, it means that we use the slope which is calculated at the midpoint, so at position of xi plus half. So the slope that is calculated at this point is taken, and that will be used to approximate the value of xi plus 1 from the value of xi here. So this is the midpoint method. So that we can see here that those two methods is actually a higher order Runkuta method, in which if we have the Runkuta method, in general, the Runkuta method use this approach in which we can approximate the value of yi plus 1, yi plus 1 from yi plus the slope. Yeah, so phi here is the slope times h, which is the length or the interval. Yeah, wait for a moment. Yeah, so if we see here that if we want to calculate the slope, yeah, so it can contain one term or two terms or more. Yeah, so that how many terms that is included in the calculation of the slope, that will define the order of the method. Yeah, so if, for example, we use only one term here, So A1, K1. So A1 here is the coefficient, K, A is a constant, and K1 here is the slope, which is taken at xi, yi. Yeah, so K is the slope which is taken at xi, yi. So if we use only one term, it means that we will have the Euler's method. Yeah, it means that we will use the Euler's method. If we use two terms, yeah, so it means that we now calculate the slope based on the value of the slope at xi, yi, and another point which is taken at xi plus p1h, yeah, so at p1h, and the corresponding value of yi. If we take three terms, it means that we will use the slope which is calculated at xi, yi, and xi plus p1h, another point in between xi and xi plus 1. And also we use another point as well, another slope as well, which is calculated at xi plus p3h. Yeah, so another point in between xi and xi plus 1. So that we will see here the calculation. Yeah, if we choose first order Runkuta, so with one variable only, or we have yi plus 1, which is equals to yi plus a1k1h, and we take k1 a1 value here is equals to 1, and k1 value here will be fxiyi, so that will be yi plus fxiyi times h, so that will be the Euler's method in which we have done that. Now if we include two terms here for the calculation of the slope. So here we have the second order Runkuta method. So in this case, we will use K1, which is the slope at xi, yi, and K2 is another slope calculated at another point here between xi and xi plus 1. So that now we can vary the value of A1, A2, P1, and Q11, yeah, so that we can have the second order method. So that if we look at the equations, we can have this constraint in which if we have the calculation of A1 plus A2, so the coefficient of A1 and A2 should be equals to 1. And the calculation of A2 P1, that will be half. And the calculation of A2 Q11, that should be also half. So that here we have four unknown, which is A1, A2, P1, and Q11. So that we have three equations. So it means that we have more unknowns compared to the equation, so that we can assume one value. If we assume one value, so that we can find the other value. Yeah. So that in this case, we have this constraint, so that we can choose an infinite number of value for A2. Yeah. So we take a value, we assume a value of A2. So if we have this value, so we can find A1, we can find P1, and we can find Q11. Okay, so we will see here the example. If we choose A2 is half, yeah, because if we choose A2 is half, and we have a constraint that A1 plus A2 should be equals to 1. So it means that if we choose this one is half, so that A1 will be half as well. So that if we use this value, so that the value of A2 is half, so this will be the result. So when we choose A2 is half, it means that we have the Huygens method, in which the value of yi plus 1 can be calculated from yi plus half of K1, which is the value of the slope at xi, plus half of K2, in which K2 here is the value which is calculated at xi plus 1, or xi plus h, yeah, which is the interval. So that with A2 is half, we have the Huygens method. If we choose A2 as 1, so that we have this one is 1, and A1 should be 0 in order to satisfy A1 plus A2 should be equals to 1. So if we choose A2 as 1, it means that A1 is 0. So then we will have the midpoint method, in which yi plus 1 will be calculated by yi plus K2 slope at another point in between xi and xi plus 1 times h. So the K2 value will be the value at the midpoint. Yeah, so xi plus half, or xi plus half h for the actual location. And if, for example, we choose A2 is 2/3, yeah, when we choose this one is 2/3, so that we have A1 will be 1/3. So that now we have the calculation of yi plus 1 that will be equals to yi plus 1/3 of k1. So k1 here is the slope which is calculated at xi plus 2/3 of k2 times h. And how to calculate k2? Because we have the a2 value which is 2/3, so that we can insert this in this correlation, yeah, to find P1 and Q11. So based on that, we have the value here now becomes K2 is the slope which is calculated at xi plus 3/4. Yeah. So if the midpoint is calculated at xi plus half, so that the Ralston method now is calculated at position I plus 3/4. Yeah. So if we have xi here and we have xi plus 1 here, so when we have half is here, so this is xi plus half. So when we calculate the slope here, so that will be the midpoint method. If we choose the value at xi plus 3/4, so it will be here. Yeah. So then when we find the slope, so this will be the slope of K2, then we can insert it here and then we can find the result. So this is for the Runkuta method. Yeah. So in this case, we have the second order Runkuta method as well. Yeah. So all of this method here is included as second order Runkuta method because it's using two terms to predict the slope. Now, if we want to increase to higher order scheme, yeah, so then we can do that as well. Now, before that, we will look at the illustration as well, similar to what we seen last week, yeah. In Hume's method, so that we will approximate the point at xi plus 1, which is here. So when after we get this point, and then we can find the slope. So the final slope will be half of the slope at xi plus the slope at xi plus 1. So that if we have the same example as before, so for example, we have dy over dx, which this is the equation. Yeah, so dy dx will be, yeah, so dy dx, so that will be a function of xi yi. So this is the function. And we want to find the solution between x0 and 4 with a step size of 0.5. So that with the initial condition, x equals to 0 to y equals 1, so this is the initial condition, use Yune's method. So this is the Yune's method. So when we want to calculate the value at 0.5, for example, yeah, so we will do marching from x0, 0.5, 1 up to 4, for example, yeah, so that we will do marching from 0 to 0.5. Now, when we want to calculate 0.5, it means we need to find the value of k1 and k2 first. So k1 will be the value of the function at xi yi at initial point. So that we have here that will be the value of x0 and yi is initial value as well as 1. So when we insert this value here is 0 and y is 1, because here in this case we don't have y in the function here. It's only a function of x in this case. Yeah, it's only a function of xi. But if we have, for example, y here, yeah, we have y variable on the right hand side here. It means that we have a function of x and y, so that we have to insert the value of y here in the variable that appears in the function. But in this case, because we don't have y variable, so that we need only x value. So we insert the x value here, so that will be 0, 0, and 0. So that will be positive 8.5. Now we calculate for k2, in which k2 here is the slope which is calculated at point xi plus 1. So that we use xi plus 1 and the corresponding value of yi at yi plus 1. Yeah, at yi plus 1. So that when we insert the value of 0 here, So that will be 0.5. And we have the value of yi plus 1. Now, in this case, we don't need y. But what if we have a y variable here, so that we have to calculate this one first? Yeah. So how to calculate yi plus 1, so that we can use yi plus 1 here, which is calculated from the Euler's method. So that will be fxi yi times h. So that if we have this one is 8.5, with h value is known, which is 0.5. Yeah, h value is 0.5, and the value of yi here is 1. So then we can calculate the value of yi plus 1. So then we insert this value, yi plus 1 here. And then once we insert it here, we can insert it into the equation, and we can find the value of the slope. So that when we calculate y 0.5, that will be equals to y0 plus 0.5 k1 here, we insert the value here, plus k2, we insert the value, times h, so that will be the final result. Yeah. So this will be the value at 0.5. So what we have earlier here, when we calculate at 0.5 with the Euler's method, this is only used to find the slope for K2. Once we have the value of K2, so that this is the final result. Yeah. So this is the final result for the position of 0.5. When we finish this with this one, so then we can continue to point 1. So when we want to continue to point 1, again, we can do the same, calculating K1 and K2 for this point. Yeah, so from 0.5 to 1, so that we can find the K1 value will be f 0.5 and y at 0.5. So that will be this value. We insert it here. Oh, sorry, no, not this value. So we insert the new value of 0.5 here. Sorry, yeah, we insert the value of 0.5 and we insert that in the function. So we have the value of K1. And how to calculate the value for K2? Again, we do the same. So that will be F1 and with Y1. What is the value of Y1 here, which is not known yet? So this is calculated with this one. So Y1 from the Euler's method, that will be equals to Y 0.5 plus F 0.5 y 0.5 times h. So once we have this value, we can insert it here, and then we can calculate K2. Again, to calculate y1, yeah, so calculate y1, so that will be equals to y 0.5 plus 0.5, the average of K1 and K2, the new value of K1 and K2 here, times h. So that will be the new value for y1. Okay. So this is for the Hume's method. Yeah. So this is the example of how we do the calculation with Hume's method. Okay. Any question?
Not yet, ma'am.
Excuse me, ma'am. I want to ask something.
Yes.
For the process that we determine the value of K2, if I look for the apa namanya itu selalu pakai K2 itu sama dengan fx plus xi plus 1 sama y plus 1, tamen.
Yeah. Yeah. We always use this one. Yeah. So we always use so that K2 value. So for example, we have xi and xi plus 1. Yeah. So K2 is always calculated at this point. Yeah. While K1 is this point. So this is K1 and this is K2. So this is always calculated at xi plus 1. And if the function contains y, it means that this should be the value of yi plus 1. What if we don't have the value? So we can find it from the Euler's method first. Yeah. Yeah.
Because on your slide, it's a little bit confusing for Rungi Kutta. When I read it, to determine K2 is the function of xi plus p1h. Yang itu, yang fungsi xi terus plus P1HY1. Itu
Ini,
makanya saya bingung tadi pas.
ini.
Ya, yang sebelumnya, Mem. Yang sesudahnya apa ya? Yang cari K2-nya.
Yang ini.
Oh, berarti yang sebelumnya, Mem. Yang sebelumnya tadi.
Sebelumnya, yang mana ya?
Nah, sebelum ini lagi, Mem.
Sebelum ini.
Ya, sebelum ini lagi.
Ini Euler's method.
Bukan yang di slide yang week 12-13.
Week 13.
Nah, itu kan ada di setelah improved Euler's method, itu kan ada Runge-Kutta method.
Ini.
Setelahnya lagi. Satu slide lagi.
Ini bukan.
Nah, itu, Mem. Nah, itu saya rada bingung tadi kan Anda jelasin kalau K2 ditemukan dari fungsi xi plus 1 dan yi plus 1. Nah, tapi di sini sedikit complicated. Jadi tadi saya, wah kok gini caranya, apa beda sama yang ini, yang K2 dari sini.
Ya, jadi sebetulnya ini sama ya, di mana P1 ini adalah nilainya jaraknya berapa ya, berapa bagian dari H terhadap XI ya, berapa bagian H dari, kalau P1 ini 1 berarti kan menjadi XI plus H, berarti kalau kita punya XI, kemudian kita punya jaraknya adalah H, maka ini adalah XI plus 1 ya. Nah, tapi bisa juga ini diambil pada jarak yang tidak satu ya. Jadi P1 nilainya P1 ini tergantung dari nilai yang kita ambil A2 dan A1-nya berapa. Seperti tadi kalau A2-nya kita ambil setengah ya. Kalau A2-nya kita ambil setengah, berarti kembali lagi ke persamaan ini tadi ya. Kita punya constraint di sini bahwa A2P1 di sini harus sama dengan setengah. Jadi kalau kita punya P1-nya tadi, A2-nya ini adalah setengah, sebentar. A2-nya tadi diambil berapa di sini? Ya, A2-nya diambil setengah ya. Jadi A2-nya diambil setengah, A1-nya 1 ya. A1-nya juga setengah ya. Jadi kalau ini diambil setengah, maka ini juga setengah. Jadi kalau A2-nya setengah, berarti P1-nya 1. P1-nya 1, berarti kembali lagi ke persamaan di sini, berarti kalau kita menggunakan A2-nya setengah, yaitu Yun's method, berarti ini harus setengah. Maka ini P1-nya tadi harus 1, makanya menjadi X1 plus H, berarti diambil pada X1 plus setengah. Ya. Maka berapa Q11-nya? Q11-nya juga 1 ya, Q11-nya juga 1. Karena ini tadi berdasarkan persamaan di sini kalau ini setengah, maka Q1-nya juga 1 ya. So that if we choose A2 is half, so it means that we use the Yun's method, and how to approximate the value, that we'll use 2 point here. Yeah, so K, the slope of K1 and the slope of K2. How to find the slope of K2? Then we have to insert the value of xi plus 1 and the corresponding value of y to the function here. To the function of dy dx, yeah, dy dx as a function of xy. So once we have the value, once we have the value of xi and yi here, yi plus 1, xi plus 1 and yi plus 1, so that we can insert it here to find the slope at this point. Yeah, to find the slope at this point. And how to find the value of yi plus 1 if we don't have the value yet of yi plus 1, because this is predicted as well. The only value that we have is only 2 point here, the initial value. So this is why this ODE is called initial value problem. Initial value problem, because we start from one initial point, yeah, for xi and the corresponding value of yi. So what we have is a value here, but we don't have the value of the function at xi plus 1. So if we don't have the value, so that we have to find it first, the value here using the Euler's method. Yeah, so yi plus 1 will be approximated by yi plus the slope at xi, yi, which is projected to this point. Yeah, projected to xi plus 1. So we have a point there. So then we can calculate the slope based on the value of yi plus 1, which is calculated using Euler's method. Okay, so that will be the explanation, Sultan.
Okay, thank you, ma'am. So the conclusion is will be the same, right, ma'am?
Yeah, the same.
For
Yeah, this
the-
calculation is the same.
okay.
Yeah. Yeah, so it's actually a further explanation. Yeah, so the calculation is the same. So this is just to show you that just as a proof that Dune's method and midpoint method are second order Rungkuta. Yeah, although the step is different, but both of these is Rungkuta. And also we learn of another method, which is called Rosen method, which is also Rungkuta method, which applying A to value, which is 2/3, so that we have this equation.
Okay, ma'am.
Okay.
Thank you very much, ma'am.
Yeah. So that is for Yuen's method, so that we will see the example for the midpoint method as well. So we can solve the same problem using midpoint method. Yeah. So the midpoint method means we calculate the slope at xi plus half, and we use the slope to approximate the value of xi plus 1 from point xi. So that if we have the example, the same example before, now with a midpoint method, so that we can calculate yi plus 1, that will be equals to yi plus the slope, which is calculated at midpoint. Yeah, so at xi plus half, yeah, and yi and the corresponding value, so that we want to calculate at xi plus half and yi plus half. Yeah, so we want to find the value of the 2 here, and that is multiplied by h. So that if you want to find at 0.5, yeah, at x 0.5, so it means that we can calculate y 0.5 there from the value of y0 plus the slope, which is using the value at the midpoint. So that will be the value at x at, which is the point at 0. If we have delta x or the step sizes or h, yeah, h is 0.5. So that will be half of h. So midpoint will be 0.25. And the corresponding value of 0.25 h. Now, if this function contains y value, so we have to find this first using Euler's method. So that will be equals to yi plus f xi yi times half of h, yeah, or that it will be equals to y0 plus f x0 y0 times half h. So that will be y 0.25. So once we have that, we can insert it there. So if this contains y, so we can insert it in the equations. So that we can have the new slope, yeah, the slope which is calculated at point 0.25. So in this case, because this is only a function of x, so we can insert that directly in the equation. Yeah. So then we can have the slope here. So once we have the slope, so that we can predict the value of the y value at 0.5. Yeah. And then we can do the same for y1 and y1.5 and so on. Yeah. So this is the midpoint method. Now next we have the Rungkuta method, the Rosen method, in which this is the illustration. So what we do is that we calculate the slope at xi, yi, and then we use this slope to predict I plus 3/4 from point xi. So we project it from xi there with the slope, and then we have this point, and then at this point we insert this into the equation so that we have the slope at this point. So this is the slope. So this is the K2 value. So the slope at position 3/4. So once we have this slope, so then we can insert it here. So the slope here can be inserted in the equation so that we can find the value at I plus 1 or at 0.5. Yeah, so that when we compare the three methods, yeah, so this is the comparison. So if we have the true solution or the analytical solution here is shown by the black line, yeah, the smooth black line, and then we have the approximation with the Euler's method. So the point here of the calculation is shown with the circle symbol, the black symbol, black circle symbol here. So this will be the solution for the Euler's method. So we see here that the error is quite large, yeah, using H or the interval size 0.5. Now with the same interval size, now we apply it to Yun's method so that we have the square symbol here. And then if we have the midpoint method, so that will be the circle symbol here. And Ralston will be the triangle symbol here. So we can see here that in this case, it looks like perhaps yeah, so we see here that in this case, probably the best will be the midpoint or perhaps the Ralston method. But in general, we can see that all of these three methods here give approximately almost the same level of error. So this is all second order method. Yeah, second order method. Which one is the best in this case? Yeah, we know that these two lines might be the best. But in other case, it might be that Ralston will be the best or Yun's method will be superior than the others. Yeah, but more or less, all of these three methods is second order Runkuta. Now we will see if we want to extend further to higher order method. Yeah, so we can have the third order Runkuta method in which we have three terms included. Yeah, three terms included. So the final result for the calculation for yi plus 1, that will be equals to yi plus 1/6 of k1 plus 4 times k2 plus k3. So we have three slopes here. Yeah, we use the weighing average of free slope, in which the highest way for the slope will be at k2. So if we look at here, what is k1? K1 here is the slope which is calculated at point xi, yi. And what is the value of K2? K2 here is the slope at the midpoint, yeah, at xi plus half. And K3 here is the slope which is calculated at xi plus 1. But be careful, what we use in y here, yi plus 1, when we want to decide yi plus 1, so what is the slope that is being used to calculate yi plus 1? So we look at here that actually the slope that is used to calculate the yi plus 1 is actually the minus k1 plus 2k2. Yeah. So the slope that is used to approximate the value at yi plus 1 for calculating k3, it is minus k1 plus 2 times k2. So we will look at the illustration. Yeah. For example, we have xi. And we have xi plus half, and we have xi plus 1. Our goal is to find the value at here, xi plus 1. What we have, the information is at xi and the yi value. So what we do first is we calculate the slope here. So for example, we have the slope, which is k1 here. So this is the slope. And afterward, we use this slope to predict the value at xi plus half. So we have this point, and then we calculate the slope. For example, we have the slope as this one. Yeah, so this is k2, for example. So then once we have the calculation of k2, and then we do the calculation here, the slope, which is minus k1 plus 2k2. So that this calculation, so we have minus k1 plus 2k2. So that will be, say, approximately, yeah, like this. So this will be more or less will be the result. So that we use this point from the value of yi. Yeah, so it means that we predict that from the value here. So we use the slope here, yeah, which is if we have the slope is minus k1 plus 2K2. Then we use it here from point yi to project it to xi plus 1. So this will be the value of the predicted value for calculating K3. So once we have this point here, which is yi plus 1 based on this slope, and then we can calculate the final slope at K3. So once we have K1, K2, and K3, so that we can insert this in the equation. So that will be the final result. Yeah, so say the final result will be, for example, like this one, say like that. So this will be projected from x1 again, xi again, yeah, and this will be projected there, for example. Yeah, so this is just a rough illustration. Yeah, it might be not like this because this is 4 times k, so this should be has the largest way, so probably like that. Yeah. So that we can see here that we need to calculate 3 slopes. Yeah, the slope 3 slopes from 3 different points. So this is third order Runkuta, and then again we can increase to fourth order Runkuta, in which we have the value at k1, which is the slope at xi yi, and then we have the value of k2, which is the slope at xi plus half, and the corresponding value of yi here, yi plus half, is calculated from the slope of k1 here. Now we have K3. So what is K3? K3 is also the slope which is calculated at xi plus half. But how the y value predicted is using the value of K2 here. So the slope at the new value of the midpoint is used to re-predict, yeah, to calculate again the value at yi plus half. So that will be K3, and this should be K4, yeah. So K4 here is the slope at point xi plus 1, in which the value of yi plus 1 here is predicted using the slope which is calculated at K3. So this will be the fourth order Runkuta. So I hope this definition is clear enough. So what is the difference between K2 and K3? Yeah, the difference is that the point of yi plus half is calculated with different slope. To calculate K2, we use the slope at K1, while to calculate K3, to calculate the slope at K3, we use K2 value. Yeah, so this will be the fourth order Runkuta. So when we see the comparison, say we have this function, and we want to solve this function. Yeah, for example, this is dy dx will be equals to this function, and we want to use the first up to fourth order Runkuta to solve the equation from x0 to x to 4. So that if we have, sorry, this is not this is the real function. Yeah, so this is the analytical solution. So that if we have the initial condition at x0, the value of y will be 2. Okay, so this one, oh, so this is correct. This is dy dx. Yeah, so the exact answer at y4, that will be 75. Yeah, so for example, in this case, yeah, so this is the analytical solution. Yeah, so this is correct, the analytical solution. So then maybe insert the value here. So that will be 75. Yeah, 75.3. So that we can compare the result at x4 here, and we can plot the relative error to the analytical solution. So we see here that we see that with the Euler method, so we can see the reduction of the error here with the number of effort. And Yoon's method, yeah, this is approximately Yoon's, the midpoint method, or the Ralston method. All of that are second order Runkuta method. Or if we use the third order Runkuta, we see that the error is greatly reduced, even fourth order. And for the Butcher method, we don't discuss this at the moment. Yeah. So this is a comparison of the Runkuta methods. So we have seen here that we can use the simplest one, which is the Euler's method. And we can also extend to the second up to fourth order to get a better accuracy for the calculation. Okay, so that will be the methods available to solve ODE, in which in this ODE we have the initial value problem. Okay, any question? Okay.
Not yet, ma'am.
Yes.
Not yet.
Okay. Yeah. So that here we will skip this one. Okay, so this is dealing with, we will not discuss that at the moment. So we will see here that we can solve, for example, problem 25.1, in which we have this ODE, and we can solve this analytically. Yeah. So this is quite easy to solve analytically. It means that we have to put together the variable. Yeah. So that you can solve this analytically. Or using Euler's method, which H is known. We have two step size, yeah, interval size 0.5 and 0.25, and we need to compare that with midpoint method, in which we have zero. The interval size is 0.5. Yeah, so this is second order Runkuta, and also we can compare that with fourth order Runkuta method with the same interval size. So we can solve that from 0 up to 2, in which we have the initial value. Yeah. So in the initial value at x0, the y value will be 1. So that for the analytical solution, we can solve that easily, so that we can combine together. Yeah, we grouping the same variable together, so that we have y. So that will be t squared minus 1.1. So that now we collect together the same terms. So that we have y now move to the left side. So that will be 1 over y dy. And that will be equals to t squared minus 1.1 dt. So that we can just do the integration as usual. Yeah, so that we have ln y, and that will be, is it 1/3 t to the power of 3 minus 1.1 t. Yeah, so that if we want to calculate y as a function of t, so that we have y, which will be e to the power of 1/3 t to the power of 3 minus 1.1 t. Yeah. So check for this. So this will be the analytical solution. Now we want to compare that with the result with Euler's method, midpoint, and fourth order Runkuta. Yeah. So I think that can be the assignment for you to work on. Yeah. So problem 25.1. Okay. So this is about ODE initial value problem. So if there is no questions, so that we can continue to the second type of ODE, which is the boundary value problem. Yeah. So this is chapter 27, which is the now wait for a moment.
Mohon maaf, Man, masih mute suaranya.